Good morning, dear students. I am your physics professor, Dr. Nagraj. So, I am going to start with the discussion of another model question paper for computer science and allied branches physics syllabus. This is on request. Many of you have requested me to continue with the discussion of model paper. Here is the next paper. So as usual, the question paper pattern, by now you know how the question paper will be, what are all the constants will be there in the question paper, all these things you know. So let us directly go to the question number 1. See, question number 1, define laser and discuss the interaction of radiation with matter. So you have to first of all give the definition of laser. Laser stands for light amplification by stimulated emission of radiation. And now you have to explain only the interaction. It is not the continuation of Einstein, complete derivation of Einstein's A and B theory. It is only 3 interactions. When light falls on the matter, what all the things going to happen? You know, there are 3 things going to happen. One is absorption and 2 are emissions. One is spontaneous emission, another one is stimulated emission. That much only you have to explain. See, first you have to define what is E1 and E2. Consider a matter or consider a system consisting of identical atoms. Let E1 and E2 be the energy levels. E1 is ground state and E2 be the excited state. When light is incident on this matter, 3 things are going to happen. They are, number 1, see, you need not have to write this paragraph. It is only a sort of introduction. Straight away you can start with the first one. Radiation can be absorbed by the atoms in the ground state. This is nothing but induced absorption. And this induced absorption is depending on the number of atoms. Next, after sometimes the atoms will go to excited state, and after spending a time of 10 power minus 8 seconds, they will come down to the ground state spontaneously without anybody's support. Therefore, it is called spontaneous emission. During the process, h nu amount of energy is emitted. This is spontaneous emission. Next, another possibility is stimulated emission. When the atom is in the excited state, and if you send the radiation right now of same frequency, the atom will come down to the ground state. So this time you will get 2 photons. This is nothing but stimulated emission. And for lasing action, stimulated emission is essential. Okay, and these 3 possibilities are diagrammatically represented like this. This is incident atom and incident photon, atom goes to excited state. This is absorption. Next, after spending some interval of time, it will come down to the ground state by emitting the photon. This is spontaneous emission. And here atom is already in the excited state, atoms are in the excited state, incident photon is inducing the stimulating the emission, so they all will come down emitting many identical photons. So whatever I explained in wordings are represented in the form of diagrams. Okay, well, define angle of acceptance and also derive the numerical aperture expression. First you have to define angle of acceptance and numerical aperture. Both you have to define and then you have to derive the expression. Well, first of all, what is angle of acceptance? This is regarding optical fiber. Here is a definition. Angle of acceptance, also called as acceptance angle or contact angle, is defined as the maximum angle of incidence of the light beam at the center of the core, up to which the total internal reflection takes place in the core clad region. See, when optical fiber working principle is total internal reflection. When you send the ray, it gets into the fiber and keeps on traveling in the zigzag form because of the total internal reflection. So this happens only when the ray is traveling at an angle, okay, of theta naught, that is called angle of acceptance. If the angle is greater than theta naught, it is not accepted. Okay, well, next is numerical aperture. Numerical aperture of an optical fiber is defined as the product of refractive index of the surrounding medium and the sine of the acceptance angle. By and large, we simply take it as sine theta naught, assuming that surrounding medium, say for example, this is optical fiber, surrounding medium is air. For air, n naught is 1. Therefore, we take it as sine theta naught. But definition, proper definition you have to give, it is not only sine theta naught multiplied by n naught, where n naught is the refractive index of the surrounding medium. So you have to give the proper definition. Well, n naught sine theta naught. Now we have to find a expression for Na, that is numerical aperture. What is numerical aperture mean? Main significance, it will explain or it will tell you about the light gathering capacity of the optical fiber, how much light it is going to accept. If the numerical aperture is more, light gathering capacity is also more. That is the meaning. Okay, well, first diagram, you explain the diagram. See, this is the center where the ray of light is falling. This line is nothing but axis of the optical fiber, and from this line to this line it is core region. Core region is having a higher refractive index and this region is clad region. It is having lower refractive index, okay, and the surrounding is air. Air is nothing but N naught, N1, N2. N1 is greater than N2, N2 is greater than N naught, and this is the theta naught, angle of acceptance. Okay, the ray of light falls at O and then undergo refraction, so it is bending towards the normal. Again there is another refraction. Suppose if this angle is greater than critical angle or equal to critical angle, the ray will graze the surface, otherwise it will go into this medium like this. So first it is bending towards the normal and then it is bending away from the normal, and because the ray is traveling from denser to rarer, if the angle of incidence is equal to critical angle, then the refracted ray will graze the surface. Now we have to apply Snell's law. 2 points, one is at O, another one is at B. Remember, this angle is equal to critical angle, and if this is theta 1, this is also theta 1, and this total angle is 90 degree. Therefore I write this as 90 minus theta 1. So critical angle is equal to 90 minus theta 1, and this is the angle of refraction for this particular ray, and that angle of refraction is 90 degree. So with this much background, you just explain the diagram in your own words. So whatever I explained, it is in wordings. Okay, so for this diagram explanation, 1 mark is reserved. Like you write AO is equal to incident ray, OB is equal to refracted ray, BC is equal to ray grazing the surface, theta naught equals angle of refraction, angle of incidence. Itara, you can explain the diagram. Then you start with the derivation. Same diagram, for the sake of clarity and continuation I have written here. That doesn't mean that you have to write diagram twice. For the explanation sake, ಇಂದಿನ ಸ್ಲೈಡ್ ಅಲ್ಲಿ ಈ ಡಯಾಗ್ರಾಮ್ ಅನ್ನೇ ಮತ್ತೊಮ್ಮೆ ಬರೆದಿದ್ದೀನಿ ಇಲ್ಲಿ. ಈಗ ನೋಡಿ ಸ್ನೆಲ್ಸ್ ಲಾನ ಅಪ್ಲೈ ಮಾಡ್ತಾ ಇದ್ದೀನಿ. ಅಪ್ಲೈ ಸ್ನೆಲ್ಸ್ ಲಾ at this point O. You know what is Snell's law? Refractive index into sine of that angle, that is N naught into sine theta naught, is equal to refractive index of the second medium into sine of the angle of refraction. So N ಇದು PUC ನಲ್ಲೂ ಓದಿರ್ತೀರಾ, N1 sin I is equal to N2 sin R ಅಂತ. I is angle of incidence, R is angle of refraction. N naught is the refractive index of this medium, N1 is the refractive index of this medium. Well, after rearranging, I get this formula, sin theta naught is equal to N1 by N naught into sin theta 1. Now I want to eliminate this sin theta 1 so that I get the refractive index, I get the numerical aperture expression, that is NA. NA is equal to sin theta naught ಅಂತ ಗೊತ್ತಿದೆ. ಸರಿ, ಇವಾಗ sin theta 1 ಅನ್ನು ಎಲಿಮಿನೇಟ್ ಮಾಡೋಣ. ಅದಕ್ಕೆ ಏನು ಮಾಡಬೇಕು? We have to apply Snell's law once again at B. Apply Snell's law at B for the next pair of media. ನೋಡಿ, ಇದು ಒಂದು ಪೇರ್ ಆಯಿತು, N0 ಮತ್ತೆ N1. ಇಲ್ಲಿ ಇನ್ನೊಂದು ಪೇರ್ N1 ಮತ್ತೆ N2. ಇಲ್ಲಿ Snell's law ನ ಅಪ್ಲೈ ಮಾಡೋಣ. When you apply Snell's law here, I already told you this is angle of incidence, that is 90 minus theta 1. So N1 sin I, that is sin of 90 minus theta 1, is equal to N2 sin R. R is already 90 degree. Well, simplify. Sin of 90 minus theta is cos theta. So I have N1 cos theta 1 equals N2. Next, cos theta 1 is equal to N2 by N1. Remember, my intention is to replace this sin theta. I have cos theta, convert cos into sin using this relation. Cos theta sin theta relation. Sin theta is equal to root of 1 minus cos square theta. So therefore equation 1 becomes, illik bandbidana, sin theta naught equals N1 by N naught as it is, sin theta place ali I write root of 1 minus cos square theta. Now cos theta is already there, N2 by N1, substitute and simplify. Well, sin theta naught equals N1 by N naught into root of 1 as it is minus as it is. In the place of cos theta, I write N2 by N1 whole square. Almost over. Simplify. Square on this n square, N2 square, N1 square, and take LCM. So N1 by N naught into root of N1 square is LCM. So numerator becomes N1 square minus N2 square. Dear students, just to go through the steps, you will get the answer. So sin theta naught is equal to, see, N1 square, N1 cancel, I left with N naught here. Next I take N naught this side, so I have N naught into sin theta naught is equal to root of N1 square minus N2 square. And what is this N naught sin theta naught? Sir, it is nothing but numerical aperture. Hence numerical aperture is equal to root of N1 square minus N2 square. Well, now I come to a numerical problem. Laser has a power output of 10 power minus 3 watt. Calculate the number of photons emitted per second. Given the wavelength of the laser is 692.8 nanometer. So we have to solve the numerical problem. Well, let us write the data given here. 1 minute. So lambda is given as 692.8 nanometer and power is given as 10 power minus 3 watt. So we have to find out the number of photons emitted per second, that means T is equal to 1. Dear students, you know energy is equal to N into Hc divided by lambda, and you know power is equal to energy divided by time. So therefore I get power is equal to N into Hc divided by lambda into T. Therefore N is equal to cross multiply P lambda T divided by Hc. I hope you got it, where T is nothing but time during which photons are emitted. So substitute for power, that is 10 to the power of minus 3, lambda is 692.8 into time is given as 1 second, whole thing divided by H is 6.62 into 10 power minus 34 into speed of light is 3 into 10 power 8. I just simplify this for you. It is 6.62 to the power of minus 34 into 3 to the power of 8. Take the reciprocal of this into 692.8 nano, that is minus 9, into 1 to the power of 10 power minus 3. So finally it comes out with 3.488 into 10 power 15. So in 1 second 3.488 into 10 power 15 photons are emitted. Since it is only number, we need not have to write any unit for this. That's all about the question number 1 ABC. Now comes question number 2 ABC. Well, question number 2A. See, first module is all about lasers and optical fibers. Therefore, question number 1 and 2 will be about lasers and optical fibers only. Illi nodi, illustrate the construction and working of semiconductor laser with neat sketch and energy level diagram. And also you have to mention the applications of semiconductor laser. So you have to talk about construction and working of semiconductor laser. Well, construction. See, look at the diagram. Semiconductor laser consists of two semiconductor pieces, N type and P type. In the diagram, P type is yellow region, N type is green region. Between these two, there is a thin layer that is nothing but junction. It is represented by violet color. This is junction. Okay. So this semiconductor slab, okay, will be having 6 faces. Say for example, 1, 2, 3, 4, 5, 6. So top two faces are connected to power supply, and front and back faces are polished and silvered. Okay, so look at this. Top this face and bottom this face connected to power supply. Front face and the back face are silvered. Among them, front face is partially silvered, back face is completely silvered. So partially silvered face is here, and once the laser is finally produced, it will escape from the partially silvered face. So it acts like a window. Alli solpa opening irutte, laser will escape through that part, and the whole lasing action happens in this junction region. So whatever I explained, it is in wordings now. It consists of heavily doped gallium arsenide semiconductor diode having P and N sections. P type is zinc, N type is doped with tellurium. This part is not compulsory. This is only optional, right? This P type, how you produce P type, how you produce N type, you need not have to mention. It is only optional, right? Next, the active medium is PN junction itself. See, dear students, in semiconductor, we need to have active medium. In active medium only entire lasing action is happening. Population inversion agodu, metastable state irodu, stimulated emission agi laser orgade barodu. All these things happen only in the active medium. In semiconductor laser, active medium is junction itself. So that is the meaning of this sentence. So PN junction is active medium. Two faces perpendicular to PN junction are polished and silvered. They act as optical resonator. Andre photon hinde munde hogi barutte. Photon goes here, hits the mirror, returns back. Hits the mirror, returns back. So the region where photons are traveling to and fro, that region we call as optical resonator. Okay, that is the meaning of this sentence. They act as optical resonator. Other two faces are parallel to PN junction and they are connected to DC source. How they are connected? Forward bias. In the sense, P type is connected to positive, N type is connected to negative, and the whole unit is very very small in size, about 1 millimeter thickness, that's all, not too big in size. Okay, now the working part goes like this. Look at the energy level diagram. This is P type energy level diagram, this is N type energy level diagram. From here to here, it is nothing but junction. This is nothing but junction. See, when P type and N type are connected, electrons enter from N type, holes enter from P type into the junction. So P type kade N type ಕಡೆಯಿಂದ electrons ಬರುತ್ತೆ, P type ಕಡೆಯಿಂದ holes ಬರುತ್ತೆ, ಅವೆರಡು junction ಒಳಗಡೆ ಇರ್ತವೆ. ಆಮೇಲೆ ಏನಾಗುತ್ತೆ, from the conduction band, electron will go to valence band. It will combine with the hole and then light is emitted. Light is emitted, not laser is emitted. This is normally happening in case of LED. LED nalli electron jumps from conduction band to valence band. It recombines with the hole and light is emitted. This is normal happening in case of LED. Suppose if your semiconductor is heavily doped, then you will have more number of electrons in the conduction band, more number of holes in the valence band. Dear students, remember, for lasing action we need more number of electrons. That means it is a sort of population inversion. So we go for heavily doped semiconductor for this purpose, in order to have more electrons there, more holes here. That is one thing. Second thing, if you increase the voltage more and more, means if you pass more current, again more electrons are injected into the conduction region. That means we want more electrons in the conduction band, more number of holes in the valence band. That we achieve by two ways. Number one, by increasing the impurity concentration. Heavily doped andre adene. So ಒಂದು heavily doped ಮಾಡಿಬಿಟ್ಟು heavy doping ಮಾಡಿ more electrons ಬರೋ ತರ ಮಾಡ್ತೀವಿ. Another one is by increasing the forward voltage, we push more electrons into the junction, that is depletion region. So as a result, I will have more and more electrons here. Normal semiconductor alli, normal PN junction alli, that is in case of LED, there will be few electrons. They come down and they emit light. But for me, it is not just ordinary light. I want more number of photons. All of them must be emitted simultaneously. For that purpose, I go for heavily doped semiconductor. I increase the forward bias voltage. So finally what happens? The number keeps on increasing here. Population inversion takes place. And then stimulated emission. Immediately after population inversion, there will be stimulated emission. As a result, the laser pulse is emitted. This is the working. ಅಷ್ಟೇನೆ. ಈ ಏನು ಇಷ್ಟೊತ್ತು ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಿದೀನೋ ಅದನ್ನು ವರ್ಡಿಂಗ್ಸ್ ಅಲ್ಲಿ ಹೇಳಿದೀನಿ. Look at this. When forward bias voltage is applied across the junction, electrons from N type enter into P region where they combine with holes, causing spontaneous emission. This normally happens in LED. ಹೇಳಿದ್ನಲ್ವಾ, ಇದು LED ನಲ್ಲಿ ಆಗುತ್ತೆ. Concentration of electron hole pair is very less. Normally it is very less. In semiconductor laser, we use heavily doped, highly doped P and N types. ಹೇಳಿದ್ನಲ್ವಾ ಇದನ್ನ. Now, as the forward current increases beyond the threshold value, more and more electrons are injected into P side. ಇದು ನಾನು ಹೇಳಿರೋದು. ಇದನ್ನ ನಿಮ್ಮ own words ಅಲ್ಲಿ ಬೇಕಾದ್ರೆ ಬರೀರಿ. As the forward current increases, more electrons enter into the junction region. Hence, population inversion takes place. Hence, laser is emitted. ಈ ತರ ಬರೆದ್ರು ನಡೆಯುತ್ತೆ. Overall meaning like that only. Any one recombination of electron and hole pair triggers stimulated emission of photon, and thus emitted photons ಆಮೇಲೆ emit ಆದಂತ photon ಹಿಂದೆ ಮುಂದೆ they have to travel to and fro because their number should grow in size. Their number should grow more and more, and finally the laser pulse should grow in size. ಅದಕ್ಕೋಸ್ಕರನೇ laser photons to and fro travel ಮಾಡಲಿಕ್ಕೋಸ್ಕರ we have converted the ends into mirror. So emitted photons travel back and forth by reflection, and finally they escape to the partially silvered mirror. So whatever I explained in wordings, it is given here also. Whatever I explained about the working of the semiconductor laser is given in wordings here. Well, that's all. Coming to applications, we use semiconductor laser in laser printers, data storage devices, that is CD reader and writer, and also laser range finder. This is mainly used in defense. Okay, so that's all about question number 2A. Now coming to 2B. Discuss the types of optical fibers based on modes of propagation and refractive index profile. Types of optical fibers. There are three types: step index single mode, step index multimode, graded index multimode. Okay, so it is like this. See, in the case of types of optical fibers, two things are very important. Number one, this one, size. What is the size of the core and what is the size of the clad? A single mode fiber consists of very thin core material. Core is inner part. It is very thin, about 8 to 10 micrometer. And second point, very important, is refractive index profile. Inside the optical fiber, refractive index is very constant, very much constant. See, suppose if this is the optical fiber core region, so this diameter itself is very small, and everywhere the refractive index must be same. That I will explain afterwards using the diagram. Okay, so now you have to talk about the dimensions. Dimensions of the core is very small, whereas clad is very high, 60 to 70 micrometer. Even refractive index also, here also it is constant, but it is less than core. It must be. Clad refractive index must be less than core refractive index. And it, because the size is very small, very narrow gap irodrinda, it can support only one signal at a time, or very less number of signals. Actually one signal adu support madodu. That is why it is called as single mode optical fiber. Okay, this is the diagram. See, core is very small, about 8 to 10. Clad is big, about 60 to 70. Our refractive index profile. See, this is refractive index value. This is a diameter or radius value. Inside the core, refractive index is constant but large. Suddenly falls and remains constant once again. So core is greater than clad, but inside the core it is constant. Inside the clad also it is constant. This is about single mode. Next, coming to step index multi-mode. Again size. This time core is little bit more bigger than single mode. See, diameter is 50, goes up to 200. Now it is no more a small region, it is widened now, 50 to 200. Correspondingly even clad also, ಹೊರಗಡೆ region ಕೂಡ ಜಾಸ್ತಿ ಆಗಿರುತ್ತೆ. Corresponding clad is 100 to 250, right? But refractive index profile is similar to single mode only. Means it is constant, decreases, constant, decreases. So it looks like a step. So refractive index profile ಒಂಥರ step ತರ ವೇರಿ ಆಗುತ್ತೆ. See, it remains constant and then decreases, remains constant, decreases. Even this side also remains constant, decreases, remains constant, decreases. Nodi, this looks like a step. That is why it is called as a step index profile. Okay, so the diagram, okay, graded also I will explain. Then I will come to the diagram. See this one. See, this is core region. Core is 50 to 200 and the clad is 100 to 250, but refractive index profile is step variation. Okay, and because it is big in size, the core region is big in size, it can accept multi signals, many signals. That is why it is called as multi-mode refractive index, multi-mode optical fiber. Coming to graded index. Graded index is also called as GRIN. In graded index, core is big, about 50 to 200. Correspondingly clad is also big, about 100 to 250, but the difference is, that means it is similar to step index multi-mode only, but the difference is core refractive index is not constant. It consists of layers of different refractive indices. Optical fiber in a core region in a refractive index, so constant irodilla. It is a continuously variable one. So refractive index does not remain same. See, this part is no more constant like this. It keeps on decreasing, gradually decreases and then remains constant. So because of that, it is called GRIN. Look at this diagram. See here, optical fiber refractive index is decreasing in this region. It is decreasing in a gradual manner. Afterwards, it remains constant. Because of that, it is called as graded refractive index or graded optical fiber. So in this region also, in this case also, diameters are same as multi-mode step index. But the difference is not in the size, but in the refractive index profile. In case of multi-mode step index, refractive index varies in step, whereas in the graded index, it varies gradually. That is why the name graded, right? So that's all about the types of optical fibers. Now, numerical. Obtain the attenuation coefficient of a given fiber of length 1500 meter given input and output powers are 100 milliwatt and 70 milliwatt. Dear students, in problems of this type, remember length is always substituted in kilometer. L is equal to 1.5 kilometer. And then P input is equal to 100 milliwatt. Always input power is more than output power. Output power is 70 milliwatt. We have to find out alpha, that is attenuation coefficient. So alpha is equal to minus 10 log of P 10 by L log of P input divided by P output divided by P input. Okay, so that is equal to minus 10 divided by 1.5 into log of P output is 70 milliwatt divided by input is 100 milliwatt. Simplify, this is minus 10 by 1.5 into log of 70 by 100, that is log of 0.7. Log of 0.7 is minus 0.154. So already minus sign is there, so you just multiply by 10 divided by 1.5, it comes out to be 1.03. I just do it once again. 10 into 0.154 divided by 1.5, it comes out to be 1.026. 1.026. Just 1 minute. Okay, so 1.026 decibel per kilometer. This is the answer for this particular question. Okay, let us move on to the next one. Now it is module 2. Module 2 is about, just 1 minute, module 2. Okay, I will continue with the module 2 in my next video. I will stop here. Thank you very much.